بسم الله الرحمن الرحيم. Dear professors, colleagues, and students, welcome again, and thank you for being with us today in the third keynote session of ICSSD conference, Dr. Kaoutar El-Maghraoui, who will present a talk titled Accelerating, Optimizing, and Automating AI Across the Stack, Current Landscape, and Future Directions. But first, let me introduce Dr. Kaoutar El-Maghraoui. So, she's a principal research staff member at the IBM Watson Research Center in Yorktown Heights, New York. She is a member of the AI engineering research team at IBM Research AI, where she is working on research at the intersection of systems and artificial intelligence. She leads the end-user AI testified of the IBM Research AI Hardware Center, a global research hub focusing on enabling next-generation chips and systems for AI workloads. In her prior roles, she has conducted research on several aspects of the AIX operating system, such as performance, multi-thread, and multi-core scheduling, flash SSD storage, OS crash diagnosis and recovery, interactions with systems architecture, and applying machine learning techniques for OS problem diagnosis and prediction. Kaoutar has co-authored several conference and journal publications in the area of system research, distributed systems, and high-performance computing. She obtained a PhD degree in computer science in 2007 from Raytheon Polytechnic Institute, Troy, New York, and a master's degree in computer science in 2001 from El-Maghraoui University, Ifrane, Morocco. She was a lecturer of computer science in the School of Science and Engineering at El-Maghraoui University in 2001 and 2002. Kaoutar has received several fellowships and awards, including the American Association of University Women Fellowship, the Robert McNaughton Award for Best Thesis in Computer Science at RPM, IBM's Eminence and Excellence Award for Leadership in Increasing Women's Presence in Science and Technology, and IBM's Trier 2 Award for contributions to the foundational power software technologies and promoting these systems in Africa. She's a member of the IEEE Computer Science Society, Society of Women Engineers, and the ACM. Professor El-Maghraoui is very passionate about mentoring and promoting the participation of women in STEAM fields. She is a chair of the Arab Women in Computing Arab Week Anita Borg Institute Sisters Community. So, Dr. Kaoutar El-Maghraoui, the floor is yours. Thank you.
Thank you. Can you hear me? Hello, can you hear me?
Dr. El-Maghraoui?
Can you hear me? Hello? Can you hear me?
Yes, go ahead.
Okay, great. Let me share my screen. Can you see my screen?
Yes, thank you.
Thank you so much for the introduction. It's a pleasure to be here. I just want to make sure that you still can hear me. Hello?
Yes.
Okay, great. So my name is Kaoutar El-Maghraoui, and my background from my PhD days they've been distributed systems and high-performance computing. But my current interests, they lie in efficient deep learning techniques with a focus on AI automation across the life cycle of AI applications and also across the stack. I'm part of the IBM Research AI Hardware Center, leading our testbed infrastructure efforts and working closely with our clients, our partners. In this talk, so I'll give an overview of some research directions that we're pursuing in the AI Hardware Center, especially focused on optimizing and automating and scaling AI across the stack, the current landscape and also future directions. So before I start my talk, I just want to give a quick overview about IBM Research. So IBM Research is one of the largest and most influential corporate research labs with an unmatched investment in basic research and also core science, and a big commitment to invent the future of technology by making scientific breakthroughs that will transform industries and society. So this just figure here just shows some highlights, where more than 3,000, scientific and technical researchers working worldwide. Lots of achievements, so far since, across the history of IBM. Some notable ones like 6 Nobel laureates, 10 national labs medals, national medals of technology, 5 national medals of science, 6 Turing awards, which is the equivalent of a Nobel Prize in computer science, and also leadership in as being the #1 patent producer worldwide. So this is, a global research capability across many labs across the world. And you can see here the locations of our different labs worldwide. So we have labs in the US, in Africa, in Australia, in Europe, in Asia, and so on. And also the activities of our labs reflect both local market needs and also the deep technical expertise found in these regions of the world. For example, in our Dublin lab in Europe, Ireland, it collaborates, this lab collaborates with academic industrial partners on research programs established by the European Union, as well as collaborative projects developed side by side with the University of College Dublin scientists. And in Africa, we're developing commercially viable solutions to transform lives and also spark new business opportunities in key areas such as agriculture, healthcare, financial inclusion, education, energy, blockchain, and cloud computing. So this is just some highlights, of some of the key focus areas that you can see here across the different labs. And another thing I would like to emphasize that we also have a long history of innovations in AI. As all know, AI is not a new field. It's been around for many decades, but it really took off very recently with all the recent advancements and innovations in deep learning. So if you look at the history of scientific innovations at IBM, we have really a tough act to follow here. So the first working chess program happened at IBM in 1957, and also some of the first demonstrations of machine learning in the checkers program, and also first demonstrations of a neural network and reinforcement learning in the complex domain like the TD Gammon game, which is a computer backgammon program developed in 1992 by Gerald Tesaro at IBM's T.J. Watson Center. And its name comes from the fact that it is an artificial neural network trained by a form of temporal difference learning, specifically TD lambda. And more recently, the first computer to debate humans convincingly, which is a big project that we have at IBM Research in 2018. This was featured. So going, to the topic, switching gear here to the topic for today's discussion. So I want to start by highlighting the tremendous need that we have for efficient deep learning. AI, and especially deep learning, has achieved incredible performances in numerous fields, including computer vision, speech recognition, natural language processing, etc. However, with this huge success also comes increased complexity. If you can see here first, the thing that we notice is deep learning models, they're getting larger and deeper with millions or even billions of parameters. In fact, the number of parameters in deep learning models is increasing on the order of 10x year per year. And this is a graph, that was shown by Intel in Intel AI conference, which shows basically the huge increase in the number of parameters. You see here these models, for example, GPT, with the NLP, the latest models, they have trillions of parameters, billions of parameters. So these number of parameters that are increasing kind of exponentially here, they're just increasing they're translating rapidly increasing compute. Which brings me to my second point. So this increased size and the complexity of deep learning models translates eventually into high computational demands. In fact, compute requirements for AI training jobs have been doubling every 3.5 months. I mean, if you think about what we've been noticing, lately, this is really a big, tremendous increase. And additionally, most of these models are too expensive to computationally train on devices, for example, like cell phones, embedded devices, or edge devices. And in addition to that, the third point that we see here, that with this increased computational cost and also increased model complexity, also comes the increase in carbon footprints and the high costs. So researchers, for example, at the University of Massachusetts at Amherst, released in 2019 a very startling report that estimates that the amount of power required to train and search a certain neural network architecture involves the emissions of roughly 626,000 pounds of carbon dioxide, which is equivalent to nearly 5 times the lifetime emissions of the average car in the US, including also its manufacturing. So really, if we keep going at this rate, we are going to consume the entire energy budget of the world just to train AI models. So, I mean, all of these things, putting them together, we can see that we really need to start thinking about not just increasing the accuracy, getting the best models in terms of accuracy, but also how do we shift from thinking about state-of-the-art accuracy to state-of-the-art efficiency. And as the future of AI is moving, especially to the edge, and AI becomes increasingly important at the edge, we need to consider more efficiently this shift of basically having more efficient deep learning models. Learning at the edge, and especially with reinforcement learning and other techniques, will play a key role in the future. And edge intelligence, if you see here, it also comes with a lot of challenges, such as resource-constrained devices that have, for example, CPU, memory, power, etc. They're really constrained at the edge. The difficulty also of deploying these models on a fleet of these devices or a large number of devices. Also, the instability of the connectivity in the network, being able sometimes to work with these AI models even if you don't have connection. So you really have to have some backup option or fall-off option when you have no network connection. And also the fact that data, also there are some privacy concerns, and sometimes data cannot leave the device in many cases. So often you have to deal with, okay, how do I use these AI models in these constrained devices, maybe being able to retrain these models on the flight, and also obtain real-time performance without having to compromise also the accuracy of the model and still deal with all of these real-time and practical constraints. So in this grand landscape of building efficient neural networks, we see 3 approaches come into play. The first one is increasing model efficiency through the design of accurate and efficient neural networks. What we call here, how do we work on building models that are efficient? The second approach is increasing hardware efficiency. And here, the work is focusing on building purpose-built AI hardware models that are really built to train and serve these models in a very efficient manner. And the third approach here is design efficiency. Basically, how do we automate the design of efficient neural networks through neural architecture search? Basically being able to automatically generate efficient neural architecture networks that are designed for certain target platforms, certain constrained hardware platforms. So I'm going to go briefly just to kind of brush on some of the approaches in each one of these 3 topics: model efficiency, hardware efficiency, and design efficiency. So let's start with the first one. So with regards to model efficiency, some of the popular approaches include things like pruning, compact convolution filters, reduce precision computations, and knowledge destinations. So let me explain what each one of these things mean. And each one of these things is basically a whole research topic on its own. And given the time, I don't have time to go into details on each one of them, but I just want to give you the landscape of these different techniques. So the first one, pruning. So the goal of pruning is basically to optimize the model by eliminating the values of the weight tensors And the aim here is to get computationally cost-efficient models that take less amount of time in training, and also a way to reduce the size of the neural network through compression. So after the network is pre-trained, then it is fine-tuned to determine the importance connections. So here the idea is we want to figure out what are the important connections in this neural network to keep, and then prune the others that maybe will not affect the the resulting accuracy of the network that much. So in the compact convolution filters, this is especially useful in computer vision domain. So what we're trying to do here is optimize the downsampling and reduce the number of channels and kernel sizes that we use in computer vision neural networks. For example, reducing the number of channels and the kernel sizes from 3x3 filters to 1x1 filters. That's one example, but there are many other techniques that are used in compact convolutions. The other technique is quantization, or also what's referred to as reduced precision. And the fundamental idea behind quantization is that if we convert the weights that you find in neural network and inputs to integer types, here we consume less memory for all the multiply, accumulate operations that happen in the hardware. And these operations also are done much faster. You don't need the full precision. You don't need 32 bits to represent these weights. And you can get away with the accuracy that you're going to lose, or the precision that you're going to lose, because deep learning in general is very a probabilistic in nature and statistical in nature. And often you care about averaging across a large number of values. So sometimes you can get away with losing the precision, that really fine-tuned and fine-grained precision, by just having less bits, less bit widths to represent these numbers. And the last technique here is knowledge distillation. And here what it refers to the idea of model compression by teaching a smaller network step by step exactly what to do using a bigger and already trained, a bigger and deeper already trained network. So the soft labels here, they refer to the output features maps by the bigger network. And after every convolution, for example, layer, and the smaller network is then trained to learn the exact behavior of the bigger network by trying to replicate its output at every level. So think about it like you have a teacher and then a student, and then you have a teacher model, which is a big model, and then you have a student model that learns from the teacher model. So these are, some popular techniques that are used especially to build efficient models and design accurate and efficient neural networks. So the other technique here is hardware efficiency. And so what are we doing here in this space? And it is a huge area of investment and focus also for us at IBM Research, is to imagine the future of AI, computations, and realize it beyond the world of graphical processing units, or GPUs, which are kind of the standard today for accelerating neural networks computations. GPUs are the best examples of things that we have today, but by no means they are the ideal architecture to implement some of these AI architectures. So that's, really the focus of what we do at the AI Hardware Center. So to address this, in February of 2019, IBM Research launched the Research Collaboration Center to drive next-generation AI hardware accelerators. And this was like a big investment made by IBM, but also New York State, to invest $2 billion. And also New York State committed like $300 million as well over the next, 5 years from 2019. This generated a lot of interest in the technical community, and also really this is a very serious endeavor by the IBM Research and also IBM Research Company to build an ecosystem of enterprise and academic partners to drive next-gen AI hardware accelerators. So what we do, in the AI Hardware Center, we're working across the stack. We take an interdisciplinary approach, looking at hardware, system software, algorithms, and also like deep learning frameworks and so on, looking at things like, okay, how do we design digital AI cores with reduced precision? I mentioned quantization briefly, and other architectural tricks that can help run efficient neural networks. And also looking even beyond digital computations, looking at analog AI to exploit in-memory computing devices. The next thing also is a lot of algorithmic tricks and techniques, things like reducing precision scaling, sparsity exploitations, quantization-aware training, model compression, hardware-aware neural architecture search, and so on. And all the way up in the stack, of course, all of this needs to be complemented by a lot of optimizations at the compiler level, and also doing kind of hardware software co-design to help drive, and take advantage of all of the tuning and optimizations provided by the hardware exposed to the software level. So here I show here our roadmap, IBM researchers' roadmap for what's beyond the GPU. And so what we plotted in this graph is some existing and projected performance metrics of mostly a GPU hardware that exists on the market today or has been announced by major players in the industry. And as you see here, there has been steady progress of the rate of 2.5x per year over the last few years. So the question here is, what technology do we need to develop and be able to continue this this rate of progress and even go beyond the GPU? So this shows basically the year, but also the projected or the existing gigaops per watt. And this is a very important metric because power is very important. So we need to be able, how much, operations or floating point operations that we can do per an energy unit, because that's really going to be important to be able to run these models, especially in constrained devices. So, so to be able to continue this progress, the first techniques we're exploiting is approximate computing, which basically at the core of this is using a reduced precision or quantization, which I talked about briefly. And then the other, to continue this progress here, like if you see the yellow dots here, is we want to explore things beyond digital computations, and here going back to analog computations, and I'll explain that in what's next. And this would basically give us an additional 100x improvement in energy efficiency compared to digital computations. So first technique here, or set of techniques, as I mentioned, is really exploiting new AI cores and chips that can be used for many new cloud to edge applications across multiple industry. So, and really this relies on basically exploiting reduced precision or quantization. And we're working on building new chips that basically exploit, this technique. And actually, there has been a lot of progress in this space by our teams, by our algorithmic team and digital AI course team in this space. So we also have been leading in reduced precision scaling while maintaining ISO accuracy, meaning with less bits that we use to train for training and also for inference, we're still able to get the same accuracy as you would get on a full point precision, like 32-bit. IBM research team proposed, the first reduced precision neural network training and started this precision scaling journey. Precision scaling has been very effective for hardware performance improvement in these years. So every 3 years, we've shown here that arithmetic precision has been scaled by 2x, which improved 4 to 6x hardware performance without losing network accuracy. So, and in 2018 and 2019 at NeurIPS, we had successfully shown our first 8-bit training and continue leading precision scaling. In inference, we also showed the first demonstration of 2 bits and 4 bits training. And this has been published in really top conferences like ASICS and SysML and other conferences here, NeurIPS. And at more recently at the ISSCC 2021 conference, we had a highlight paper where we demonstrate IBM test chip based on 8-bit training and 4-bit inference. So, and it's very important to know here that reduced precision improves energy efficiency quadratically. Every time, you know, you scale down the bits, you get quadratic improvements in energy efficiency, which is very important. And there is also a wide coverage by the media about, you know, what's we've accomplished in the last few years in terms of demonstrations for the first tiny 4-bits computer that you can use to train AI, and also our AI chip, which is leading in the world in precision scaling. And there are references here that you can check offline if you're interested. So the next step in the evolution of specialized hardware for AI is really rooted at addressing the performance efficiency loss that we get from data movements between computational units in the memory. So let me explain what I mean by that, and also what is analog AI all about. So analog AI, or what we call here non-volatile memory, or NVM technology, what it does is it enables memory computing, which eliminates the Van Neumann bottleneck, which is the fundamental problem that we're still having, which basically, and also in memory computing, what it does, it allows you to do computations directly in memory and avoiding the movement between the memory, the CPU, the bus, and so on. So how this is done, this is accomplished by mapping the neural network to analog hardware, and then storing the neural network weights that you find in deep learning as a property of the material itself. So this results in eliminating data movements altogether, and this can result in unparalleled speed up and energy efficiency for AI workloads. So let me explain at a very high level how this is done conceptually. If you look at digital accelerators today, they're typically set up like this. There is a processor on one side, and then there is the memory on the other side, and they're connected by a bus. So, and this is actually what we refer to as the classical Van Neumann architecture. So let's say that you want to multiply two numbers, A and B. So they start first by sitting in memory, and then they're sent to the processor through the bus. The computations happens in the CPU, and then the answer is sent back again to memory through the bus. And this is actually what causes, you know, consumption of a lot of energy in digital processors today. Additionally, this bus can become a big bottleneck, especially if you have to deal with lots of computations, especially in neural networks. As these models become bigger and bigger, imagine, you know, the strain that this causes on these computational units. Analog accelerators, on the other hand, get rid of the processor and do everything in memory itself. So how this is done is basically, you know, you have A stored in memory, and then you send B, which is the value that you want to do some computation with A, you send it as a voltage. So let's look how this, you know, and then you get the outputs. So all of this is basically done using the laws of physics. So let's look, you know, how really a dot product, for example, can be accomplished in analog. So first look, you know, consider this simple circuit shown here on the left. You have 3 wires and you have 2 resistors, right? Let me just show it here. 3 wires here, and then 2 resistors, and each one of these resistors has conductance G1 and conductance G2. So assume that these 2 resistors have these conductances, and then if you apply a voltage V1 and a voltage V2 at these 2 wires, then what happens here is the first wire injects a current V1 times G1 into the vertical line. Similarly, the second line injects a current V2 times G2 into this line here. So these currents, what happens, they add up to give a total value of V1 times G1 plus V2 times G2, which is the current I1 plus current I2. And so this resulting current in the vertical line is simply, you know, the dot product of the input vector of voltages V and the vector of conductances G. So all here what we're doing is we're applying the laws of physics So applying Ohm's law and then applying Kirchhoff's law to do the additions here. So if we extend this concept further and create a dense grid of resistances which can be programmed beforehand to give us a matrix of conductances G, when I apply a vector of voltages V as an input, what happens is, using the law of physics, Ohm's law and Kirchhoff's law, then I get, this matrix multiplication, V times G. So the current coming out are the result of a vector matrix multiplication. And this grid of resistances is what we call an analog cross-point array. So this is fundamentally the concept behind, analog AI computations. And if we want to look how basically a typical neural network is mapped, as computations from input X to the upstream neurons to a downstream neuron Y. So the vector matrix multiplications operations, basically what they do is they first multiply each element in an X vector with the corresponding weights. This is basically what happens in a neural network computations. There is a forward pass and there is a backward pass. So you have, weight, for all of these connections between the neurons, and then you have to apply, this summations across all of these multiplications between the weights, the inputs, and then the weight values, and then you have to keep doing it layer after the layer. And then you need also to add some bias. So, the details of all of these matrix vector multiplications. So a vector matrix multiplication, basically, it first multiplies each element in an X vector with the corresponding weights, and then the multiplication results are summed up over all of these elements. And then you have F, you apply basically this transformation F here. And if F is a nonlinear function that is required to ensure that the different layers in a DNN, they don't basically become one linear layer. So basically the activation functions. So how this is done, we map each element in X to the word line rows of M of a crossbar array. I showed basically you put all of these things together, and each weight is then mapped into two devices. There is a plus and the minus. I'm not going to go into the details how this is done in a chip, but just to give you a high-level idea. And then basically, so doing the multiplication and then the additions, like I showed in a simplified manner, it's just a matter of doing this, Ohm's law, and then the resulting things becomes the output of all of these values, multiplied together and added together. So the sum is performed by Kirchhoff's law that I showed, and this just basically shows that all of these computations kind of magically happen. I provide inputs on the left, and in parallel, several neurons over here are doing all the necessary math with natural summations, of course. So for an n by n crossbar, this array that you see here, the energy of each operations scales as the number of memory elements. So you have the complexity of big O of n squared. Because this is because the crossbar performs this entire computations in one step. Imagine you're injecting these pulses or these voltage pulses, and then all of these computations all are happening in parallel. Not like in digital computations, you have to each time, send across, the CPU through the bus from the memory and so on, and then you have to, and there is some caching that happens. So here, you push these voltages, and then suddenly all of this matrix multiplications happens in one step. So we have so far what we've shown kind of an analog engine that performs the dot product computations, which are the bulk of computations in deep neural networks. And these analog units, actually, one of the complexity we have, they're not precise because, this is physical, they have physical properties. They're always, they're not as precise. And there's also some overhead that's associated if we want to, attach this to some digital peripheries. So there is some digital to analog conversion that needs to happen, and analog to digital conversion, etc. And this is not a trivial circuit to build, and we have like a large research team that are just focused on how do we design and build the right analog chip. So what I've shown so far is just one way, how analog AI computations can be applied to solve, the deep neural networks computations, and how this is all done in physicals, using the laws of physics, which makes this process much more efficient, much more faster, and also energy efficient compared to how it is done in digital. So one material that is used to construct these arrays is called phase change memory, or PCM. And each PCM material basically is sandwiched between this overlapping and vertical wires on two metal layers. And this is basically sometimes also referred to as the resistive processing unit, or the RPU cell. So this just gives you an idea of what is an analog crossbar array. And basically, how do you map a DNN to analog hardware? So each one of these layers can be mapped to one or more crossbar arrays. So an analog or in-memory computing chip typically consists of multiple crossbar arrays of memory devices that communicate with each other. And the neural network can be implemented on at least one crossbar array, depending on the size, of the neural network, and in which the weights of the layers are stored as a charge or conductance of the memory devices at each one of these cross points. And so this kind of gives you very high level. I mean, this topic could take hours to explain, but I just want to give you very high level of how this is done at a conceptual level. So what we've done, we've built what we call an AI hardware accelerator kit, which is a first and also open source toolkit that enables someone to master, understand, and also accelerate with analog hardware computations. And the goal of this is basically just to how to build and power more sustainable AI models. Innovations that AI is driving in hardware. So we've recently announced, this kit, and also, as I mentioned, we open sourced it. And this toolkit uses the PyTorch framework, the deep learning framework. It also has full GPU support, and it provides a suite of tools to enable one to master and accelerate neural networks with analog hardware technology. So you can simulate basically what it would take to take a normal neural network and then run it in an analog device. So the toolkit allows understanding, exploring, and using the capabilities in memory computing devices in a simulated manner. And also it gives you access to the open source libraries. And there is also a companion no-code experience. So we have a cloud experience that allows you to basically drag and play. You can construct a neural network. You have maybe like convolutional layers, the equivalent of those in analog. You have linear layers. You also have the equivalent of those in analog. And then you can send an experiment and run your neural network in analog fashion and get the results. So this basically shows a quick demo of how you can do this. And there is actually, we have the link. I have the link in the slides if you're interested in exploring this at your leisure. So basically there is a component here that allows you to specify the properties of your neural network, but there's also an analog component where you can specify which device you would like to simulate, because there is a wide range of devices that you can simulate. There is phase change memory, there is resistive access memory, there is other devices that the research community are exploring for analog computing. And then you can submit your experiments for training, and we're also working on an inference experiment, and then you can get the results and also compare them with the baseline once finished. So that's just a quick example. I hope you get to explore this and also to explore the toolkits, the open source library behind this, which basically allows you to understand more in depth analog computations and also this emerging field. So I'm going to switch now to talk about design efficiency. And basically, what's happening here in this space to automate the design of neural networks that are efficient. So this is the third approach, and here the idea here is, how do we automate synthesis for these emerging and existing AI hardware? Today, a lot of the work, especially in auto AI, is focused on optimizing for better accuracy, model accuracy. But when we have basically reduced energy and less latency, we need to account for these metrics. Basically, how do I create a neural network that is still gives us the best accuracy possible, but can result in reduced latency and also does not generate a big energy footprint. So the space of what is called here neural architecture search is really an important step here. A neural architecture search has been widely explored, but not in a hardware-aware manner. So today's neural networks, they're very complex, and also they keep growing in size. And all the ML techniques that the community have looked at, they really catch up with human experts. So they can automatically generate neural networks that can match or even exceed the performance of neural networks that are hand designed and handcrafted by data scientists. And you can see here, in this figure, some results where basically you get the performance of the auto AI is almost matching the performance of the humanly or handcrafted neural networks. When we look at handcrafting neural networks, it's really an expensive and time-consuming process. If you look at these flagship neural network architectures like ResNet and transformers and so on, it takes many years of PhD experts to really come up with these really nicely crafted and designed neural network architectures. So it's not a trivial task. So auto AI tries to automate that. And if you look also at edge intelligence, this is not on the requirements. As I mentioned before, this hardware efficiency built into the design of neural network and this software-hardware co-design, which is a very hard task for non-hardware experts and typical data scientists or neural network designers that don't have to worry about, okay, am I going to run this on a CPU or a GPU or on another accelerator on the edge? Where is this going to run? So they just want to really focus on building a model, given a data set that gives me the best performance without having to worry about the details of where is this going to deploy. So that's, what hardware-aware neural architecture search tries to do, is kind of bridge that gap and make it easier to generate these neural networks that are automatically tailored for hardware. So I've done a collaboration with the University of Polytechnique Hauts-de-France, and the goal here was basically to address some of these questions. What are the key algorithmic components of hardware-aware neural architecture search? And what search spaces are more friendly to hardware? And also, what are the existing challenges and future directions? This survey is available online, so please take a look at it. And basically, this kind of allowed us to understand the current landscape of what's going on. So if we look at hardware-aware neural architecture search, so this is basically, it's a subset, of auto ML. And auto ML is kind of this bigger field where you're looking at, in general, automating machine learning. Part of that, there is the hyperparameter optimization, and part of that, there is the neural architecture search, where you're basically trying to find the best architectures for neural networks. And then a subset of that is hardware-aware neural architecture search, where you're automating the design that's deployed in especially more constrained devices that's aware of the target platform. So this just, shows quickly the trends that we see here in terms of the targeted platforms in hardware NAS, and also the types of network that has been considered. So there is a big focus. I mean, if you see here across the years, I mean, GPU, there's still a big focus, but we also see here that there are more increases in other platforms like FPGAs. They're gaining more attention, and you know, no specific target is just more emphasis on FPGA. You know, ASICs also are, you know, increasing in terms of the focus here. And there's a lot of work, you know, in building, you know, these next-gen or, you know, specialized accelerators for deep learning, like the work we're doing, you know, with analog and with the reduced precision chips. But lots of startups and companies are also looking at their building their specialized, you know, ASICs or FPGAs for deep learning across multiple domains. In terms of, you know, what type of networks are being looked at, so NAS has focused a lot on standard CNNs, like convolutional neural networks, when it started. And the performance of neural architecture search has been really very good with CNNs and even extended CNNs. But right now we see there is more also work in transformers, more recently looking also at RNNs, you know, for speech, but, you know, additional types of CNNs like capsule CNNs and MLPs. So these are just the trends. So if we look at a general neural architecture search architecture, so basically there is an architecture space, search space that you need to search through. And this basically consists of what are the types of connections or layers that you can support. For example, convolutions or poolings or activations. And there are different types of convolutions and also different types of kernel sizes and so on. So, and different types of activation functions. So you have this search space that you construct. And when you're searching, you kind of pick from this search space and try to construct these neural networks, evaluate the performance, and then backtrack again. So how do you search? There are different algorithms. So there is reinforcement learning, there is evolutionary algorithms, but there's also gradient-based algorithms that uses the gradient descent approach to search in this space. And then after you search using this search technique, you can evaluate the model accuracy. And the model accuracy basically just to give you how good the model that you've searched for is. And you use that as a metric to give the feedback to the search algorithm. In terms of the evaluation, there are different techniques. Some of them, they look at the full training. Some of them, they do partial training and use the results to inform the search algorithm. And some of them, they just build, you know, predictors or models that would predict, you know, what the performance of the model is. So there are lots of, you know, design exploration and different design points here to consider when you're constructing a neural architecture search. If you want to look at that from a hardware-aware perspective, you know, there are additional components that needs to be added. So the search space could be augmented with hardware search space. Like if I have if I know my target platform, then there are some, you know, additional parameters I could also take into considerations, like the number of processing elements, the tiling of the parameters. Like if I have an analog chip, maybe, you know, the different crossbar arrays that you have, some operations of the hardware. The search algorithm is similar to, you know, to what we've seen before, but when you look at the evaluation, the cost of the hardware, you know, here plays an important role. Like not just, you know, the accuracy in terms of the model accuracy, but you also have to look at how is this going to perform on the hardware? Do I have some real-time constraints? My latency should be less than maybe 1 microsecond, or my energy consumption should be less than this number of watts, and so on, because you have a real platform where you want to deploy this model, for example, say for inference, and you're really constrained by the physical properties of that. So then, you know, all of that becomes, you know, kind of a multi-objective optimization space where you have to consider multiple objectives, and you need to find the model that best meets the constraints. I think we're almost out of time here, so I'll try to move a little faster. So in the search space, there are also like different search spaces to consider. So for example, for the architecture, there is a layer-wise search space. or a cell-based search space where the operations in a block, like basically you have a cell that has a predefined set of operations, and you want to be able to select, this cell and repeat it. And there's also a hierarchical search space or a hyperparameter search space. So lots of different, design points here. And then for the hardware, there is a template-based. Basically, you select from a set of predefined templates or parameter-based. You have certain parameters or configurations like the tiling parameters that, best suits an FPGA used, or the number of processing elements, or the register file size in an FPGA, and so on. So this kind of shows basically how this can be also a single versus multi-objective optimization that you need to solve. For the single objective optimization, you can use typically a two-stage method. You search for the best in terms of accuracy, and then the constraint optimization, basically you consider the hardware cost in addition to in your optimization problem. And you can also formulate this as a multi-objective optimization and then use colorization methods to basically turn this into like one function here where you have multiple objective terms like accuracy, memory, and energy. Or you can also use the evolutionary algorithm that considers multiple objectives. So I'm just showing at a very high level here how this can be formulated mathematically into multiple types of optimization problems that need to be solved. In terms of the evaluation techniques that are used for the cost, there are again multiple techniques. There are real-time measurements, like if you have access to the hardware, you can take the sample model that you've searched for, and then you execute it in the hardware while you're searching. So these are just show some of the techniques or the papers or research efforts that have used these techniques. And then the lookup table, or you have your hardware and you've construct ahead of time a lookup table that you create beforehand, and this lookup table basically will give you for each operation, like this is a convolution operation, or this is like layer-wise convolution, or different compact convolution, and so on. What is the cost on your hardware? There are also some low fidelity estimations, like we can compute a rough estimate using the processing time, the stall time, and the starting time. Kind of you estimate the cost of both latency, energy, memory footprint, and even the chip area. Or you can build a prediction model, which basically gives you predicts the cost using an architecture and dataset feature. So this is also, you have to build it. You construct a data set, and then you build a model that predicts what would be the latency, for example, given these types of architectural features. Anyway, so I've only scratched the surface here. Again, you have a reference. I can provide the reference to the survey, which really digs into more details. And this is still a very evolving field with lots of challenges and lots of open problems. The search space here, NAS, just starting with neural architecture search, this is a very hard problem, and it's a very expensive problem too. And when you add to that, the hardware complexity, it becomes even, you have a combinatorial explosion of the search space. So, and especially if you consider additional strategies like quantization and pruning, if you can even add those to the search space. And then the other thing is also the high computational cost of the search strategy. You have to search in this huge search space. So that becomes very expensive computationally. Benchmarking and reproducibility. Right now, there are very few hardware NAS benchmarks. Hardware NAS bench is the first hardware benchmark that was published very recently at ICLR 2021 this year. And another thing is basically the transferability of these AI models, especially across these different search spaces. And also the transferability of hardware NAS across multiple platforms. You can create an algorithm that works maybe for this type of FPGA or this type of embedded device. But can I transfer that? Can I reuse the same technique or the same model? or components for on a different hardware. So that is also a challenging task. And right now also what we see is most of these existing approaches, they're very limited to computer vision applications, very little work happening in the space. But this is emerging. So some of the key takeaways here, this hardware NAS is still a hard problem and still exists, to how do we take this and then generalize this. And then the other thing is lack also of generalization I just mentioned, especially, across different modalities. Right now, a lot of focus on vision, but we need this, to look at natural language processing, at speech, which are becoming very important applications. And also techniques that we saw that really stand out. Layer-wise search seem to be more hardware friendly than cell-based search spaces. And also the differentiable techniques, they're especially the ones that use weight sharing. They seem also to have a lot of promise, especially because they're much more efficient in exploring the search space using gradient descent-based method. And also using predictors for predictions for hardware costs, they also can mitigate some of the costs of really running on, having access to the real hardware at hand. So this is also a very good technique. And quantization aware and pruning aware predictors, they're also, gaining more popularity in the space, especially as many platforms are taking advantage of this reduced precision for training and inference. So, this is just kind of a summary of, kind of summarizes all these different techniques in terms of efficient deep learning methods, which are really inevitable and important. And this is still an evolving landscape that I mentioned. Lots of techniques that look at model compression. Also there are techniques that look at code transformation, which are non-hardware agnostic. There are also the ones that are hardware agnostic, like compression, hardware usability. We want to maximize. And also in the middle here, the hardware-aware neural architecture search, which basically tries to search for architectures that maximize accuracy and also tries to maintain hardware usability. So this is just a quick summary here that puts all of these things together. And that brings me to the end of my talk. I thank you for your attention and happy to take any questions.
Thank you, Professor El-Maghraoui, for this rich presentation. And now we will pass to